Welcome back, everybody, for another deep dive. Today, we are going to be looking at how to make your GPU code as efficient as possible. And we're going to be doing that by taking a deep dive into the concept of coalesced memory access.
Yeah.
We're going to be referencing a recent article called Coalesced Memory Access in CUDA for High-Performance Computing. And it's really all about getting the most out of your hardware when you're doing these kinds of computations.
It really is.
So-
CUDA stands for Compute Unified Device Architecture, and it's a platform and programming model from NVIDIA
Right.
that allows developers to harness the power of GPUs for general-purpose computing.
And GPUs, of course, are known for their graphical processing power.
Right. Yeah.
But with CUDA, we can actually leverage that parallel processing power
Yes.
for a wide range of general-purpose computing tasks, not just graphics.
Absolutely. That's right. Like scientific simulations,
Yeah.
machine learning, even cryptocurrency mining.
Yeah, crypto mining is a good example because it is so computationally intensive.
Yeah.
And that's exactly
Yeah.
what GPUs are good at.
And that's where, efficient memory access comes into play.
Right.
While GPUs are incredibly powerful, their performance hinges on how efficiently they access memory.
That's a really good point because you could have the fastest processor in the world,
Yes.
but if it's constantly waiting for data, it's not going to be able to reach its full potential.
Exactly.
And that's where coalesced memory access comes in.
Yeah.
So what exactly is it?
Okay, so imagine a group of threads
Okay.
called a warp,
A warp.
all needing to grab data from the GPU's memory.
Okay.
If they're all fetching data from sequential locations,
Uh-huh.
that's coalesced access. It's like a bus picking up 32 passengers all at once.
Okay, I like that analogy.
Yeah.
That makes a lot of sense to me. So
Yeah.
it's like everyone gets on the bus quickly, efficiently, and then we can go to the next step.
Exactly.
What happens if the memory accesses aren't coalesced, though?
Then it's like that bus having to stop for each individual passenger.
Oh.
We call this uncoalesced access, and it creates a bottleneck slowing down the entire process.
Yeah, you don't want to have that bus stopping every
Yeah, you want to keep that data flowing.
2 seconds to pick up a new person.
Exactly.
You want it to just
It's much less efficient.
go.
Yeah.
So coalesced access is like the superhighway
Yes.
to efficient GPU performance.
It is.
Now, the article that we're referencing here mentioned that a CUDA kernel.
Mm-hmm.
Now, for those who don't know, a kernel is essentially a function that runs on the GPU.
Yes.
That a CUDA kernel with coalesced access ran twice as fast as one with uncoalesced access.
That's right. And they give a very specific example. In their example, the kernel with coalesced access completed in 232 microseconds,
Wow.
while the uncoalesced version took 540,
So more than double.
more than double the time.
Wow.
And so that's a very significant difference. And when you think about somebody who is working with massive data sets
Yeah.
or complex simulations, that difference in performance could be huge.
Yeah, it could translate to hours or even days saved.
Absolutely. You're able to do these kinds of things in a smart way.
Yeah.
So how can we actually ensure we're getting that efficient bus ride?
Well, the first principle is aligning threads with the memory layout.
Okay, so making sure each thread grabs the data in a nice
Exactly.
orderly fashion.
Exactly. If thread 1 accesses the first element in an array,
Uh-huh.
thread 2 accesses the second, and so on, that's ideal for coalesced access.
Gotcha.
The GPU can fetch all the data that Warp needs in a single transaction.
But what if the data isn't naturally aligned that way?
Right.
The article also mentions something called shared memory,
Yes.
which acts like a cache on the GPU chip.
Right. Shared memory can be a real game changer, especially when dealing with more complex or irregular memory access patterns.
Yeah.
Because it lets us stage data in a way that allows for coalesced reads and writes,
Yeah.
even when the original data layout isn't ideal.
Okay, so it's like setting up a staging area where threads can quickly grab what they need without creating that bottleneck. That's a great way to put it. Think of it as a super efficient loading dock where threads can kind of load up on data before heading out to do their processing work.
This is really interesting stuff.
Yeah,
But I have a feeling there's more to the story,
there is.
right? The article also mentioned bank conflicts,
Yeah.
which can occur when using shared memory. So what are those?
Okay, so shared memory itself is organized into banks.
Okay.
And if multiple threads try to access the same bank simultaneously, it can lead to conflicts.
Ah, so too many threads trying to squeeze through the same door at the same time.
Exactly.
Okay.
These bank conflicts can slow things down, but thankfully there are strategies to avoid them.
Yeah.
One common technique is padding.
padding.
Adding a bit of extra space in our shared memory arrays.
Okay,
This ensures that threads are accessing different banks
gotcha.
and avoids those collisions.
So it's like adding a little extra space
Right.
between hungry people at a buffet
Exactly.
so that everyone can grab their food
Right.
without elbows flying.
Precisely. It's a simple but highly effective way to keep those memory accesses flowing smoothly.
I like it.
Yeah,
All right, so we've covered a lot of ground here.
we have.
But I'm curious, how does this actually play out in a real-world application?
Well, the article used the example of optimizing a matrix transpose operation.
Okay.
And in a matrix transpose.
A matrix transpose, now that sounds familiar from linear algebra.
Yes.
Could you refresh my memory on what that is exactly?
Absolutely. So in a matrix transpose, we're essentially flipping the rows and columns of a matrix.
Okay.
It's a very fundamental operation used in a variety of applications, from image processing to machine learning.
Gotcha. So if you're working with large matrices,
Yeah,
this optimization could really make a difference.
absolutely.
So what do they do to improve the performance then?
So they started with a basic kernel implementation, but it had a mix of coalesced and uncoalesced memory accesses.
Okay.
First, they introduced shared memory to achieve coalesced writes,
Okay.
which gave a nice performance boost.
So by staging the data in shared memory, they were able to make those write operations much more efficient.
Exactly. But then they took it a step further and fine-tuned their shared memory usage
Okay.
to eliminate those pesky bank conflicts we talked about earlier.
Ah, right. Making sure that those threads weren't all trying to squeeze through that same door at the same time.
Exactly.
Did the article say how much faster they were able to make the matrix transpose?
They did. The initial kernel took 1.61 milliseconds.
Okay.
With shared memory, they brought it down to 1.1 milliseconds.
Okay.
And finally, by resolving those bank conflicts,
Yeah.
they achieved a blazing fast time of 0.79 milliseconds.
That's incredible. That's a really significant improvement.
It is.
And it really highlights just how important these optimizations can be in squeezing every bit of performance out of your GPU.
Absolutely. And these principles apply to a wide range of operations, not just matrix transposes.
So if someone is developing CUDA code, what should they be thinking about?
First and foremost, be mindful of those memory access patterns. Are you accessing data sequentially?
Right.
Are your threads working together efficiently?
Yeah.
These are the questions to ask yourself.
It sounds like really understanding how the data is flowing through the GPU
Yes.
is key to writing
It is
performance code.
Absolutely. It's all about visualizing how those threads are interacting with memory and then using the tools and techniques we've discussed to optimize those interactions.
So you're becoming an architect of the data flow within the GPU.
Exactly.
Awesome.
Right?
Are there any other common pitfalls or best practices you'd recommend?
Well, one thing to remember is that shared memory is a powerful tool,
Right.
but it's not a magic bullet. It's finite, so you need to use it strategically.
Okay.
If you try to cram too much data into shared memory, you can actually end up hurting performance.
Oh, wow. So it's a balancing act.
It is.
Using it effectively,
Right.
but not overdoing it.
Exactly. It's all about finding that sweet spot for your particular application. Another thing to keep in mind is that these optimizations are often iterative.
Okay.
You might start with a basic implementation and then progressively refine it as you identify bottlenecks and areas for improvement.
So profiling your code
Yes.
and understanding where those bottlenecks are is crucial.
It is. And there's some great tools out there
Yeah.
that can help you visualize memory access patterns
Yeah.
and pinpoint areas where your code is spending too much time waiting for data.
Okay, so continuous optimization and analysis
Absolutely.
are really key to achieving truly high-performance CUDA code.
It really is a rewarding journey. As you become more adept at optimizing memory access, you'll see your code run faster and more efficiently, unlocking the true potential of your GPU.
It's amazing how such small changes can make such a big difference
It is.
when you're working with this kind of
Yeah.
hardware and software.
Absolutely.
Well, we've taken a deep dive into the world of coalesced memory access and explored how it can transform GPU performance. We've got a lot more to talk about, though.
Yeah.
So we're going to take a quick break, and we'll be right back. All right, so we're back, and we're talking all about making your GPU code as efficient as possible.
Yeah.
We've been diving deep into the concept of coalesced memory access in CUDA
Right.
and how to use shared memory strategically to really boost performance.
Absolutely.
But, as with anything, there are always potential pitfalls.
Yeah.
And one of the things that the article mentioned were these bank conflicts
Yes.
that can occur when using shared memory.
Right.
Can you explain a little bit more about what those are and why they're a problem?
Yeah, so shared memory itself is organized into banks.
That way.
And if multiple threads try to access the same bank simultaneously,
Yeah.
it can lead to conflicts. So it's kind of like, you have a bunch of people trying to go through the same door at the same time.
Right. It's a bottleneck.
Exactly. It's a bottleneck. And those bank conflicts can really slow things down.
Yeah, I can imagine.
But luckily, there are strategies to avoid them.
Okay.
One common technique is padding.
Padding.
Adding a bit of extra space
Okay.
in our shared memory arrays.
Gotcha. So you're kind of spreading things out a bit, but
Exactly.
giving them a little more breathing room.
Giving them a little more breathing room and ensuring that threads are accessing different banks and avoiding those collisions.
So it's like, if you have a bunch of people at a buffet,
Yeah,
you don't want them all bunched up in one spot.
right. You want to spread them out a little bit.
You want to spread them out so that they can all get to the food they need
Exactly.
without, bumping elbows.
Without bumping elbows. That's a great analogy.
So simple, but so important.
It is. And it can make a big difference in performance.
Yeah, I bet. So in the article's example with the matrix transpose,
Yeah,
did they use padding to address these bank conflicts?
they did. They actually showed a specific code example
Oh, cool.
where they added padding to a shared array.
Okay.
And it was a very simple change, but it made a significant difference.
I'm always amazed at how these seemingly small tweaks
Yeah.
have such a big impact.
They really can. It's all about understanding the underlying architecture and how the data is flowing.
Right. It's like you're fine-tuning the engine.
Exactly. You're fine-tuning the engine to get the most out of it.
So beyond padding, are there any other strategies for avoiding bank conflicts or just general best practices for using shared memory effectively?
Well, one thing to remember is that shared memory is a finite resource.
Right.
So you need to use it strategically.
Don't go overboard.
Don't go overboard. If you try to cram too much data into shared memory,
Yeah.
you can actually end up hurting performance.
Really?
Because you're creating contention and you're limiting the amount of parallelism that you can achieve.
So it's about finding that sweet spot.
It's about finding that sweet spot.
Exactly.
Using enough, but not too much.
Using enough but not too much. That's a great way to put it.
All right, so we've talked about coalesced memory access.
Yes.
We've talked about shared memory bank conflicts, padding,
Right.
all these really important things for optimizing GPU performance. Absolutely.
Now I want to take a step back and talk about something that's really important to both of us.
Yeah.
And that's the ethical implications of all of this.
Right.
Because, as we develop these increasingly powerful technologies, it's crucial to consider how they're being used
Yeah,
and the potential impact they can have on society.
absolutely. And this is something that the authors of the article touched upon as well.
Yeah, they mentioned that these optimization techniques
Right.
can be used for a wide range of applications,
Yeah.
some of which are beneficial
Yes?
and some of which are potentially harmful.
Absolutely.
So,
yeah.
for example, these techniques could be used to accelerate scientific research,
Right.
which could lead to breakthroughs in medicine or renewable energy.
Absolutely.
But they could also be used to develop more sophisticated weapons systems
Right.
or to enhance surveillance capabilities.
Yeah, it's a double-edged sword.
It really is. And it's important to have these conversations, to think critically about the potential consequences of the technology we're creating.
And to ensure that it's being used for good.
Exactly. So I think it's important for all of us,
Yeah.
whether we're developers, researchers, or just members of the public,
Right.
to be aware of these ethical considerations
Absolutely.
and to engage in these discussions.
Yeah.
Because ultimately, the future of technology is in our hands.
It is. And it's up to us to shape it in a responsible and ethical way.
Well said.
So as we continue to explore these powerful optimization techniques,
Yeah,
let's keep these ethical considerations in mind.
absolutely. All right, so we've covered a lot of ground here.
We have.
We've talked about coalesced memory access, shared memory,
Right.
bank conflicts,
Padding.
and the ethical implications of all of this.
Absolutely.
But there's still more to discuss.
Yeah, there is.
So we're going to take a quick break and we'll be right back.
Welcome back to the show, everyone. We've been talking about how to make your GPU code as efficient as possible. And we've covered a lot of ground.
Yeah, we have. We've talked about coalesced memory access, shared memory bank conflicts, padding, all those great
Those are
things.
those good things.
But I think it'd be helpful to take a step back
Yeah,
and just recap the key takeaways for our listeners,
absolutely.
because there's a lot of information here.
There is.
So what are the things that people should really walk away from this deep dive remembering?
Okay, well, I think first and foremost, remember that coalesced memory access
Yeah.
is all about getting those threads to work together in harmony,
Okay.
accessing memory in a coordinated and sequential manner. It's like having a well-organized bus route where everyone boards and disembarks quickly.
I love that analogy.
Right.
Yeah, it really paints a picture.
Yeah,
So we want to avoid those situations where threads are accessing memory in a scattered, non-sequential way.
right, because that's where you get the bottlenecks.
Exactly.
That's where you get the slowdowns.
And then, of course, we talked about shared memory,
Yeah.
which is like that on-chip cache that can help us achieve coalesced access,
Right.
even when the data isn't perfectly aligned.
It's like setting up a staging area where threads can quickly grab what they need without causing a traffic jam.
Exactly.
Yeah,
And that can be a real game changer.
it can.
But of course, we have to be mindful of those bank conflicts,
Right.
those situations where multiple threads are trying to access the same bank simultaneously,
Yeah.
which can cause contention and slow things down.
It's like having too many people trying to squeeze through the same narrow doorway at once.
Right. And the solution to that, of course, is padding,
Padded.
adding a little extra space to our shared memory arrays to avoid those collisions.
It's simple, but it's effective.
And that's really what we're all about here.
Yeah.
Finding those simple but effective ways to
Absolutely.
really boost performance.
And I think another key takeaway is that optimizing for performance is often an iterative process.
Right.
You might start with a basic implementation
Yeah.
and then progressively refine it as you identify bottlenecks.
Right. So profiling your code.
Yes,
Understanding where those bottlenecks are is crucial.
absolutely. And there are some great tools out there
Yeah.
that can help you visualize those memory access patterns
Yeah.
and pinpoint those areas where your code is spending too much time waiting for data.
Yeah. Those tools are invaluable.
They are.
The matrix transpose example that we talked about
Yeah,
really drove that point home.
it did.
By simply restructuring how the data was accessed.
Right.
They were able to achieve a really substantial speed up.
It's amazing what you can accomplish
It really is.
with a little bit of understanding and some clever optimization techniques.
So I guess the challenge for our listeners out there who
Yeah.
are writing CUDA code
Mm-hmm.
is to take a look at their own code
Mm-hmm.
and see where they can apply these principles.
Absolutely. Think about those memory access patterns.
Yeah.
Are your threads working together efficiently?
Are you using shared memory strategically?
Right.
Even small tweaks can make a big difference.
They can. And don't be afraid to experiment. And iterate optimization is a journey.
Absolutely.
And the more you understand these concepts, the better equipped you'll be to write truly high-performance GPU code.
Well, this has been a fantastic discussion.
It has.
A huge thank you to our expert for guiding us through this really complex topic
It's been my pleasure.
and for sharing all these valuable insights.
Happy to do it.
And to our listeners, thank you so much for joining us on this deep dive
Yeah. Thanks for listening.
into coalesced memory access and CUDA,
I hope so too.
and that you're inspired to go out there and write some truly amazing GPU code.
Absolutely.
Until next time, keep experimenting, keep learning, and keep pushing the boundaries of what's possible with high-performance computing.
And keep those GPUs humming.
Exactly.